Good evening, sir. Let's wait for a few more minutes and see if others are joining.
Sir, good evening, sir.
All right, I think we can start now. Okay, so good evening, all. My name is Umair Hussain. I am a PhD scholar in the Department of Mechanical Engineering, IIT Madras, and I welcome you all again to the doubt session of the course Basics of Finite Element Analysis Part 2, which is a continuation to its the Basics of Finite Element Analysis Part 1 course. where we laid the foundation of the finite element method and various concepts related to it. And here in this course, we are continuing on those foundations, and we studied couple of new things. Like we started with error approximation, the sources of various errors, and how to compute them. Uh, and then the next thing we studied was numerical integration. And initially focused only on 1D numerical integration, and so then after that we started with the 2D FEM. So initially we studied how to what kind of general statements do we have in a 2D problem, the general differential equation, and what different kind of problems can be studied from them. And then we started with the discretization of the 2D domain, and how possible errors can occur due to that discretization. We studied then we studied Last week we studied various type of approximation functions for the in 2D elements, mainly triangular elements and the quadrilateral elements, the two mostly used type of elements in FEM. And then we studied the how to formulate basic element level equations, and how to find the element level stiffness matrix and force vector. So, continuing to that discussion, in week 7, we started with the assembly of the element level equations to finally get to the global metrics and vectors. So, in assembly of 2D elements, one thing I might have mentioned a couple of times before is the concept of connectivity matrix. So, a connectivity matrix contains the data of the order of nodes which constitute an element. So the number of rows essentially are equal to the total number of elements, and the column data contains the sequence of the node values for each column. So, so basically, the size of the connective matrix is equal to the total number of elements times the maximum number of nodes in an element. So I have discussed this concept quite a few times. I might have discussed a few problems also, even in 1D as well. So suppose if we have this domain here, which has one triangular element and another quadrilateral element. So based on how we are numbering the local nodes, we will fill the connectivity matrix. I think I discussed this last time also. Someone mentioned that we need to know the local node numbers. So here, the ones written inside the elements in blue color are the local node numbers, and based on that we fill the connectivity matrix. And then we will be able to tell which elements have which nodes in common, and with the help of this we'll able to add up our element level equation to the net global equation. So in just like in 1D also, we studied two conditions when assembling the element level equations. First is the continuity equation, so which focuses on the displacement value. So displacement at the node value, which is at intersection of two elements, is going to be same. So just like in this case, for first case we have the global node 2, this one, which is at intersection of both elements. So for element 1, the global node 2 is the local node 2 of element 1, and for element 2 it is the local node 1 for element 2. So we can, so both these terms are same, both these displacement value are supposed to be same. That's what continuity means. And similarly we have one other node which is common, that is the global node 3. So global node 3 is equal to the local node 3 of element 1 and the local node 4 of element 2. That's how it works. And the second condition that we have to fulfill is the balance of forces. So the force contribution from each element is summed up on the respective common node. So at global node 2 here, the element level contribution from local node 2 would be added. The force contribution would be added with the force contribution of local node 1 of element 2, and that sum would be placed at the respective value of the global node 2 in the force vector. Similarly, the same thing would be done for global node 3. And just like the case of this body force vector, we have same for the q vector also. So that contribution would be same. However, for if the Q3 node is an internal node and no external boundary condition is applied on this node, these nodes, then the net force would be equal to 0. So this will be very helpful when we are assembling these equations. So this is the same thing that we studied in the 1D assembly. That's nothing new. So all right, so that's how basic assembly of element level equations is done for in 2D. Just to quickly revise the concept of our 1D. There was one nice problem I did earlier. So we have this kind of system where this is rigid plate and three bars are connected by this rigid plate in this such a way. So we have this as node 1, so node 2, and since this is rigid plate, these all would 3 would be node 3, and this is node 4. So essentially we'll have three elements here. So suppose this is element 1, this is 2, this is 3. So can someone tell me what would be the connectivity matrix for this system? First of all, what should be the size of the this connectivity matrix here?
3 cross 2.
3 cross 2. Yeah, right. So we have total 3 elements. So that means 3 rows. And we have total two maximum two nodes in an element. So I'll write L1 local node 1, local node 2, L2. So what should be the connectivity matrix for this case? So I'll just write the local node numbers 1, 2, 1, 2, 1, 2. So what should be the connectivity matrix?
1,
1,
3,
yes, 3,
2, 3,
2, 3. That's right.
and 3, 4.
Yeah. Thank you so much. Yes. So this is the basic concept. That's same in 1D and that's same in 2D. Okay, so this was all about assembling the matrices and vectors. We might see some few problems on this for more understanding later. Then the next thing we studied was heat transfer in 2D, basic heat transfer problem. So we might have discussed the differential equation for heat transfer problem before also. So this is what it should look like in terms of vector. I'll write, I'll expand this term here. So where U is our temperature and F naught is heat generation per area, basically heat generation density. And they're given this problem, and we'll see how to solve such problems in using FEM. So we have been given a square domain, which where its one extreme point is at -1, and another extreme point is at 1, 1. So it's a 2 cross 2 square, and at each face of the square is a given a zero temperature. That's a boundary condition. So there's one new concept that was introduced here, that about the symmetric problems. So a problem can be is considered to be a symmetric problem about any particular axis if the following properties are also symmetric about that axis. So number one is the geometry. That's obvious. And number two is the material property. So yeah, material should also be symmetric about that given axis to behave symmetrically, right? Otherwise, our equation would be different for that area and different for that area. And the next thing is the boundary condition should be same. And lastly, the force term, the force distribution there should also be the same. Force distribution here means F naught term for this equation. So such if all so not few of not just one of these, all four of these conditions should be satisfied for the problem to behave as a symmetric problem. So then we can reduce the problem. We'll see how. So this particular problem has all four symmetries about the x-axis and the y-axis. That is y equals 0 and x equals 0. So we can break it this along this line and also along this line. So it's sufficient if we just solve for this area. This way we'll have to solve on lesser area, and we'll have to consume less computational power for this. So that's how the reduced problem should look like. So we have now a domain range just which starts from at one end from 0, 0 and another end at 1, 1. So it's a 1 by 1 square now. And so we again break it into four elements. That's a discretization for FEM. And now one thing interesting about this, what should happen at the bisected planes, what should be the boundary condition of the bisected planes. So that this was obvious that these boundary conditions should remain same as they were before. But what should be the boundary condition as at the other two faces? So there a simple concept was explained that since this was the original domain, so the x-axis and y-axis, and at any 2 points, since they are symmetric, so consider this point P, this point Q. So displacement, the value of the solution at point P will always be equal to point Q. So since the solution is since the problem is symmetric, the solution is supposed to be symmetric. And as these points will come closer, this condition will hold until this P and Q are at a very small distance. That means at just right the boundary of the domain, I mean this plane, uh, the the slope of solution would be zero. So for this case, the slope in x direction would be zero, or I'll write partial. That's better to write. Or in this plane, slope in y direction would be zero. So it's better to write for any general plane. It's better to write should be equal to zero. So so this should though, so we'll have the this kind of bound, that is the Neumann boundary condition on the bisected planes. So now our problem is reduced. We have the reduced domain. We have know the boundary conditions. Now we just need to solve the problem. So we have discretized our square domain into four squares, and we know the approximation function for these simple square elements. So we have already derived the function for the stiffness matrix and the force vector that was done before. So I'm not going to go into much detail about this. We'll just substitute the values of all the approximation functions here and get the required value. So for case of quadrilateral elements, we how many equations per element we'll have four equations. Since we have four nodes, we'll have four corresponding equations corresponding to each node. But as we'll assemble for all the element level equations, so total we have four elements. So total element level equations would be four elements into four equations, 16 equations, equation per element. So but uh, how many, like one, two, three, four, five of these nodes are common, are shared between it. So ultimately we'll be left with in when after assembly we'll be left with nine equations, since we have total nine global nodes. All right. And since we have been given a boundary condition also, so we might have discussed this in 1D FEM, how to apply boundary condition and get the condensed matrix and vector. So after application of boundary condition, out of these nine nodes, we know the value of this one, two, three, four, five nodes. So ultimately, we are left with four unknown variables, that is u1, u2, u4, u5. So we know how to calculate stiffness matrix, we know how to calculate force vector, and regarding the value of the q vector, we need to look for the boundary condition. So regarding the contribution for from element node 1 and for element 1, we know the particularly for node at 4, 1 and 2, we know that there's the zero zero Neumann boundary condition there, so this term would automatically become zero. Regarding the contribution for node 5, since it's an internal node, and so the net resulting force here for that is the summation of contribution from all the four elements would be equal to zero. So thus for this given problem, the whole q vector would be zero. So now we know this vector also. Okay, so our only unknown is this, and thus we can solve these equations solve for this matrix and vector by inverting and multiplying the matrix with the force vector, and we'll get the solution for u1, u2, u4, u5. That's basically how these problems are solved. Alternatively, we can also we would have could have also reduced the problem further by applying one more symmetry. So after reduction to a square domain of size 1 by 1, we could have also reduced it to a triangle along the diagonal of the square. So if you see the diagonal here is also the diagonal here is also the domain is also symmetric about the diagonal of the square here. So you see if the boundary condition u equals to 0 and u equals 0, this is also symmetric, and here du by dn equals 0, du by dn equals 0. And material property is also, there's nothing mentioned about it being different, or the force vector is also constant throughout the domain. And yeah, so geometry is also, of course, is symmetric. So we can reduce it to a triangle of this type. Now, since we have a triangular domain, we will try to see how we can discretize into a triangular element. So we have discretized into four triangular elements and mark the local node numbers. So now we have total six global nodes and four elements. So we can try to write the connectivity matrix here. So we have four elements, and per element we'll have three equations since we have three nodes. So we have total 12 element level equations. But after assemblies, these would become six equations since we have total six global nodes. And after applying boundary condition, how many nodes would be removed? We know that the boundary condition is 0. So we have reduced three remove we know the value at three nodes u6, u5, u4. So we'll be left with only three unknowns. And of course, regarding q vector, again we can see the boundary condition for node 1, 2, and 3. All three nodes we can see the boundary condition. There's zero flux there, zero Neumann boundary condition. So that makes this whole vector 0. Again, we know the function for the stiffness matrix Kij, and we can apply the three shape functions for the triangular elements. We know that we can get the stiffness matrix. Similarly, we can get the force matrix, and we know the force vector, and we know the q vector is also 0. So we can solve the system of equations and get the value of u1, u2, u3. So that's how we can solve this problem using triangular elements. Okay, so this is how basically we solve any general problem in 2D using FEM. So the next thing that we studied was numerical integration in 2D. So we didn't in this discussion we didn't really focus about how to calculate this Kij and Fi for each element. So So to fill this discussion, we introduce the topic of numerical integration in 2D. So we had done numerical integration earlier, but that was specifically based on 1D elements. So the basic concept for the numerical integration was, so right now we are focusing only on Gauss quadrature rule. We are not talking about other numerical integration methods. Since Gauss quadrature is mostly used the numerical integration scheme. So basic funda was we had a given domain, say in terms of x coordinate, and we mapped it into a standard domain with having zeta now as your coordinate, and we used to call this a natural coordinate system. So to get the mapping function, we had this formula. Here psi I cap is your shape function, and to approximate the solution here, we had this formula. Here psi j is your approximation function. So it has been pointed out several times that this shape function and approximation might not be the same. They are conceptually two different things. So the approximation function is basically to approximate the solution, and shape function is used to approximate the geometry shape of the elements. So we have gone through this concept before also, and to get there was some important term called Jacobian here, which was basically the derivative of your mapping function with respect to zeta. Now, in case of 2D elements, we have so we since in 2D we don't have just single type of elements like in the case of 1D, we have several type of elements. So based on the element, we have the type that specific type of mapping. So like in case of quadrilateral elements, we map it to a standard square of this type where x is where zeta varies from -1 to +1 and eta varies from -1 to +1. And for the case of triangle, again we have a standard mapping which maps it, of course, to another standard coordinate triangle, standard coordinate system triangle. So yeah, so for quadrilateral element we have a separate mapping, and for triangular elements we have separate mapping. However, we have the relationship is still the same to find the mapping function like before. Now we have y coordinates and eta coordinate also. So we have another one more relation here. Just like and if we want to extend this concept to 3D system, then we would have another equation for the z coordinate also. So here in this course we are only focusing on the standard quadrilateral element. So for standard quadrilateral elements, these are the shape functions. So now we know the shape functions and we know the mapping function. One thing that is crucial in solving for the stiffness matrix is we need to know the value of the derivative of the shape functions. Since we know these psi as a function of zeta and eta only, but we need to find the derivative with respect to x. So one thing else we know is we know this relation of uh, our xy coordinates as some function of, it's not just single one function, there are two functions, of course, just representing it like that. So so that's where your Jacobian comes into action. So if we want to uh, we know these things, since we know our the shape function in terms of zeta and eta, these are known. So if we want to write the derivative of this, we can expand it like this with respect to x and y. So here also we know these because we know the mapping functions, right? Similarly, we know these. So here these are our unknowns. So what we to so in order to find these unknowns, we we need to calculate these and get the Jacobian. And of course, to solve the this given system of equation, we need to take inverse of Jacobian. So hence the important property of to for the element should be that the Jacobian that we get from that element should be a non-singular, since we want to take the inverse of the matrix, right? So in terms of layman terms, that means that the determinant of Jacobian should not be equal to zero at all points in the domain. That is important. And of course, our mapping function for eta, zeta, and eta should be continuous, differentiable, and invertible. So in order to know this thing, so our whatever element we choose should satisfy these conditions for the element to work. So that's why we saw during the week 7 lecture that such kind of element would be invalid. This kind of element will give always give a non-invertible Jacobian. And we in the initial studies, I think that was in part 1 of the course, we mentioned that such kind of element which have where if we connect 2 points, the line goes out of the element. Such elements don't work in FEM. That is, a concave surface shouldn't be there. Should always have a convex boundaried element. And one more thing that was there, one more takeaway point about this choosing the element is that the numbering of the local node should also be consistent. So if we have two elements like this, so if we were numbering this element anti-clockwise 1, 2, 3, so the next element also we should number like this, anti-clockwise. So I think this was it for the this content of this week's with this week of the course. So yeah, we studied about mapping the our element from the given coordinate system to the natural coordinate system. Okay, so this was it about this week's content. If there are any doubts, please we can address them now. Otherwise, we'll move on to the problem discussion session. I'll wait for some time for any query.
Sir,
Yes, sir.
Umar sir,
Yes, sir.
can you sketch the outline from the model equation to this? Just outline. We consider model equation. We are considering weak form.
Okay.
For that, I need the sketch. The just outline. Huh?
Sure, sure, sure. I'll try.
Here
I'll try.
up to this.
Up to this. Sure. So first of all, any FEM problem consists of a strong form, that is basically differential equation plus your boundary conditions plus a domain of the problem. So we start by writing the weak form of the problem. Okay. So then the next thing is we discretize the domain. So here we'll get our nodal coordinate plus connectivity data. Then after discretization, we uh, find element level equations. If I'm missing anything, please just let me know. You find the element level equations. That is basically we find the Kij, Fi, Qi, right? Then we perform assembly. It is basically local to global Kij, Fi, Qi. And after assembly, there's one more thing that we didn't study here in much detail. That is applying boundary condition. So then we'll get a condensed matrix. Okay, so then after applying boundary conditions, we are just left with solving the matrix and the vectors. That's it. And we'll get that result. Okay, so this is basic sketch of the whole complete FEM process. I hope this is what you asked, sir.
Sir, just is it possible to compare these steps with our week 7 material? So where we started and where we end, like
Uh, Sorry, which material?
uh, what you shown week 7 material, no?
Yeah, yeah. Okay,
Can we?
so can we identify what we consider? Yeah. So here we studied assembly. I think assembly, applying boundary condition, and these things we kind of covered. Since there's nothing much to discuss about applying boundary conditions, we have already done this in 1D. And regarding solving, we are not we are not including solving part here. That's basically solution of matrices and determinants. And here we also covered one more thing. Yeah, we also covered how to solve this thing. Basically, numerical integration here. That is not completely covered, by the way. We just introduced the concept of numerical integration. Basically, we covered the mapping part here. Mapping domain. So we covered this. Numerical integration part is still left. So that is, I think, the part of next week course. So I think we covered total this much here in this week. I hope I am not missing out anything. Is it okay, sir?
Yes, sir. Yes, sir. Yes, sir. Sir, Umar, sir.
Yes, sir.
I hope we have taken some model problem and we are applying the same weak form, discretize the domain, and we are approximating the function. Is it? Then we are maybe we are transforming the quadrilateral to the standard maybe master elements like.
Yes, yeah.
Is it right?
Yes,
So we
yes.
are now doing step 4 and 5, 6, right?
Yes,
But
yes.
anyway, we have model equation and all the procedure has been done already. Is it right, sir?
Uh, Procedure has been done in what sense? Like, I didn't
Means
get
I
it.
am asking, maybe if we are doing finite element, we have model equation. We are having weak form. We are reduced into weak form.
Yeah.
Discretize the domain like the steps you have followed.
Yes, yes.
What I am saying is, without taking that, we are just discussing about step 4 and 5. Like, is it right, sir?
Yes, yes, yes. We are
Yes.
talking
Okay.
in general sense for now,
General sense.
not for
Okay.
any
Okay, sir.
specific topic.
Okay, sir. Thank you.
Okay. So, if there are no further doubts, I think shall we move on to problem discussion? Some we'll discuss some problems based on this content. Okay, so we'll first try to practice the how to get the connectivity matrix. I mean, basically discretizing the domain. That's all. So, discretize the following domain into two triangular elements. Write the local and global node numbers. Find the connectivity matrix, and also perform the assembly of element level equations. Okay. So we'll try to do this. So since we are given a this domain and we want to discretize into two triangular ends, we can just draw this line here. So I'm numbering these nodes on my own. Okay, so we have two elements here. This is element one, let's say. This is element two. So I'll also give the local node number. This is one, two, three, and this is one, two, three. Okay. So now please someone tell me the connectivity matrix here. First of all, size of the connectivity matrix and then the values here. Anyone?
Sir, is it 2 cross 3?
Yes, yeah. So we have two rows for each element and we have local node 1, local node 2, local node 3. Three columns. So how do we fill it? For element 1, we start with node 1 is the global node 1. Node local node 2 is global node 3 and local node 3 is global node 4. For element 2, our local node 1 is global node 1, local node 2 is also global node 2, and local node 3 is also global node 3. Okay, so I hope there's no doubt with this. This is our connectivity matrix. So we have two nodes in common, you see. So next thing is we want have to perform assembly of element level equation, right? So first of all, we'll just write the general form of equation for each element. So we have for element 1 here, I'll write k11, k12, k13, k21, k22, k23, k31, k32, k33. U1, U2, F1, F2, F3. So I think similar way we can have. So in similar way we can write this for element 2 also. Okay, then we have to write a global matrix. So what should be the size of our global stiffness matrix?
Four cross four, sir.
Yeah, right. Since we have total 4 nodes, U1, U2, U4. So first we'll start with the easy one. So for global node 1, how many contribution do we have?
Two contributions, sir.
Yeah. So what are those two contribution?
K11 at first element, K11 at second element.
I am talking about the force vector. So it's right with respect to the K matrix, but I'm talking about the force vector. So yeah, right. So we have the first uh, node of the first element and also the first node of the second element. Those are the two contributions for the force vector, right? And at second node, we just have one contribution that is from element 2. So we have the second node of element 2. And at third node, we have two contribution again. So what are those two contribution? Can someone tell? I'll write the easy ones and let you guys figure out the difficult ones. So for fourth node, we have the contribution of third node of first element. So for third node, what are the two contribution? Can someone tell? Other guys can also participate. If you want to write in chat box, you can write. Yes.
Sir, F2 at 1
F2 at 1. Yeah, that's right.
and F3 at 2.
F3 at element 2. Yeah. Yeah, that's absolutely right. Thank you so much. So now coming to the more difficult part. So I think this answer was given for the first one. So for at the position 1 of global node global matrix, we have contribution from we have the 1 we have K11 for element 1 plus we have again K11 for element 2. For 2, for 1, 2, we find this connectivity only in element 2. So we have K1, 2 from element 2. And for node 3, we have again two contributions. So we have for node 3, can someone tell me? I mean, position 1, 3 of the global K matrix. 1, 3.
K12 at 1,
K1, 2 at 1.
K13 at 2.
Yes. Very, very good. Thank you so much. And for 1, 4, we also have a contribution that is K13 of element 1, right? So I hope this thing is people are following this, right? If there's any difficulty or doubt, please you can stop me. Okay, so for 2, 1, we have K21 again, 2, 1 for element 2, right? And for 2, 2, again we only have one contribution, 2 for element 2. For 2, 3, also we have only one contribution, that is K2, 3 of element 2. And 2, 4, do we have any contribution for 2, 4? Do we? So are nodes 2 and 4 connected in any element? Sorry. Hello. Yeah, sorry about that. There was some issue. Am I audible to everyone? Hello.
Yes, sir. Audible, sir. You can
Okay.
proceed.
Okay.
Yeah,
Thank
sir.
you so
We are
much.
listening to you.
Thank you so much. Yeah. So we were at the 2-4 position of the global stiffness matrix. So for 2-4 position, do we have any connectivity between node 2 and node 4 in any of the element? So if you look at the uh, connectivity matrix, so you see in none of the element we have 2 and 4 together. That means there's no contribution. 2, 4. We'll just write a 0 there. Now for 3, 1. For global node 3 and 1, we have connection. We have connection in two elements, both the elements. So first of all, 3 and 1 is K 2 1 of element 1, and we have K 3 1 of element 2, right? And for 3 2, 3 2 we have connectivity in element 2, right? And then for 3 3, 3 3 we have node 3 in two elements. So we have K 2 2 of 1 plus K 3 3 of 2. Then for 3 4 we have a connectivity in element 1. So we have K2 3 of 1. Then again, what else we have? 4 1. 4 1 is connected in element 1. So we have K3 1 for 1. And 4 2, 4 2 again, 4 and 2 are not connected. So we just write a 0 here. And then 4 3. 4 3 are connected in element 1 again. So we write K3 2 for 1. And 4 4, so 4 no, fourth node is found in element 1 only, so we write K3 3 for 1. Okay, so it got little messed up here. I'll draw a line for separation. So this is how the stiffness matrix should be assembled. This is a very simple case of two elements. So I hope this was clear. If there's any doubt, please you can ask now. So one more thing that we did discuss here, uh, that the continuity condition that we always follow. So at the two common nodes here are node 1 and 3. So the displacement at node 1 is equals to displacement for local node 1 of element 1, and this is also equal to the displacement of local node 1 of element 2. So that's how we these things come together. And then for node 3, the global node 3, the displacement is same as the local node 2 of element 1, which is same as the displacement at local node 3 of element 2. So this is continuity condition, and this is what helped us to assemble these matrices and the force vector, this matrix and force vector. So I hope this was clear here. So I hope then we can move on to the next step. Okay, so we have to do this for by discretizing the same thing into two quadrilateral elements. So again, I keep the I'll repeat this global node numbering 1, 2, 3, 4. So we have to break into two elements. We can draw this line. Now we have node 5 and 6. We have element 1 here, element 2 here. So I'll just number the local nodes 1, 2, 3, 4 anticlockwise here, and again 1, 2, 3, 4 anticlockwise here. So can someone tell me the connectivity matrix now? So what should be the connectivity matrix for this mesh? Okay, so since we have two elements, we have two rows again, and now the per element we have four local nodes. Local node 1, local node 2, local node 3, local node 4. We have four columns, so it's a 2 by 4 matrix now. So what are the elements of this matrix? So for element 1, we have connectivity in the order of 1, 5, 6, 4. For element 2, we have connectivity in the order of 5, 2, 3, 6. Okay, so we have these two nodes in common. Alright, so now again element level equations are again we'll assume some equations, some variables there, and we'll have four equations for each element, so total 8 element level equations. Now after assembly, what should be the size of the stiffness matrix K? Please, can someone answer this?
So 6 by 6 it comes, no?
Yes, yeah, thank you so much.
Oh,
So we have 6 by 6 matrix, sorry, since we have total 6 global nodes. We have no, right, node 1, node 2, 3, 4, node 5, node 6. So first we'll start with assembling the force vector. So for element 1, how many contribution do we have?
only one,
Yes,
only one contribution.
that is from
F,
element 1,
F,
from node 1
F1,
of element 1. Right, thank you so
F1.
much. For node 2, how many contribution do we have?
Single only, sir.
Yeah, that is the node
1, 2,
2 of
3, 4,
element
single
2.
only.
1, 2, 3, 4. Yeah, that's right. So for
Single
node 3, we have
only.
3 for element 2. For 4, we have 4 of element 1.
It's, for 5 only,
5, we have,
two contributions.
yeah, that would be,
6 two. That would be, oh,
so
that
one,
would be
for
F,
1 from
five.
element 1 and 2. So for what would be the contribution for element 1?
1, 5, what? So F1 plus F2 and correct.
Yeah, but
F3 plus F4, 6.
which local node
You're
is
writing
1 and 2? Uh, the superscript here means the element number, but what should be subscript? The node number.
it's an own number.
Yeah. The local node number for each element. So you can look at this. This is a node 5 here.
Oh,
So for element 1, which node is it? The global node 5 becomes which local node for element 1?
2.
Yeah, right. So that second node contribution would come. And similarly for element 2, which node will it become?
Uh, 3.
No, I'm talking about global node 5.
Fun, one. Sorry.
Yeah. That's right.
Going to F6. Okay, sorry.
Okay, so thank you so much. And for global node 6, similarly, from
3 and
element 1,
4.
3, and 4.
F3 and
Yeah, that's right. Okay, so yeah, that's how we fill the global force
force vector.
vector.
Okay.
Now, talking about stiffness matrix, I will start with 1 1. I'll just mark this. So for 1 1, node 1 is only in element 1. So we have the local node 1 1 for element 1. For 1 2, do we have any connection between 1 and node 1 and 2 in any element?
0, sir. That is.
Yeah, we don't have any connection.
1, 2, 0. 1, 3 also 0.
1 3 also 0. 1
Yeah,
4 we have.
1. No, 1, 4 we have. 1,
Yeah,
4. 1, 4. 1 we have 1.
1 4 of element 1.
Yes, sir. 1, 4. That's
Yeah,
it.
thank you so much.
Next,
And 1 5 we have
yeah. Plus,
1 2
plus
of
will come.
element 1.
1, 2
1
plus.
6 do we have?
No. 1, 6 also not there, sir.
Why not 1 6 is not there?
1, 6, sir.
1 and 6 are part of same element now.
Yeah.
Doesn't mean they have to be connected by same line, but they're part of the same element, right?
Yes.
So 1 and 6 you'll see 1 is there, 6 also there in element 1.
Yeah. In
So
first
we
row, yeah.
have
In first row, it is there. Okay.
1
Yeah.
3 of
Thank you.
element 1, right?
Okay. Sir.
Okay. So for again 2 1, 2 1 we don't have any contribution, right? For 2 2 we have 2 is only in part of element 2, that is local node 2 and element 2. And 2 3, do we have anything? Yeah, we have 2 3 in part of element 2. So 2
Okay.
3 would be again the local node number is 2 3 and part of element 2. Again 2 4. 2 4, do we have any connection?
2, 4. No. 0, sir.
0. 2 5, do we have any connection?
Yeah, we have.
Yeah. So 2 5 is part of element 2, that is K2 1 of element 2, right? 2 6, do we have any connection?
Yeah, same element, no? You told
Yeah,
me.
yeah. So 2 6 is part, it becomes local node 2 and 4 for element 2. Okay, I hope it's
Mm,
easy to follow by looking at this diagram,
mm,
right?
mm, mm.
And for 3 1, do we have any connection between 3 1?
No.
0. And 3 2, we have connection, right? That
Yes.
is local node 3 2 and a part of element 2. For 3 3, we have
Mm.
only in element 2, that is third local node. And 3 4, do we have any connection between 3 4?
3, 4. Second element, sir. 3.
3 4, the global node 3 and 4, are they connected?
Yes. No. No. 3,
No.
4.
Yeah, 3 and 4 are in separate
Correct?
elements, not in same
Separate?
line. So we'll have 0 here, right?
Oh, okay.
And 3 5, do we have? Yeah, we have connection between 3 5, right?
Yes.
So 3 5 is K3 1 of element 2. And 3 6 also we have. Is
Yes.
K3 4 of element 2. Now 4 1. 4 1 we have connection. that is K for 1 of element 1.
Mm-hmm.
For 2 is for 2 is also no, for 2 is connected or not?
No, no, zero.
0. And
Oh, that's sir.
for
Zero, sir.
3 for 3
Yeah. Oh,
for
three is
3
connected, sir.
no, 4 3 are also not in the same element.
Sure.
4 3 is also 0, right?
Mm.
And for 4 we have node 4 in only element 1, that is fourth local node. And for 5, do we have any connection?
4, 5.
Yeah,
Yeah. There's 4,
that
5.
is part of element 1, right?
Element. Yeah. Mm.
So that is the local node 4 2 of element 1. And for 6, do we have?
Mm.
For 6 also we have. That is 4 3 of.
Sir, inside are local, outside is global, no?
Yes.
That is, whatever you drawn inside the diagram, 1, 2, 3, 4, 1, 2, 3, 4 inside. Outside
Yes.
6 are global.
Yes,
Okay,
right.
okay, okay.
And
Mm.
then for 5 1, we have a connection between 5 1. That is 2 1 of element 1.
Mm.
For 5 2, we also have a connection that is 1 2 of element 2. For 5 3, also we have a connection that is 1 3 of element 2. For 5 4, also we have a connection.
Yeah.
So 5 4 is K 2 4, right, of element 1.
Same element.
And 5 5
6, 5,
5
5.
5, how many contribution do we have for 5 5?
Uh-huh.
5 is there in element 1 and 5 is also there in element 2. So 5 5 basically is K22 of element 1,
Okay.
and it's also there in element 2. For element 2, it's the local node 1, K11.
Oh,
And 5 6, so 5 6 is connection is also there in both elements.
both elements.
So 5 6, there's not much space, I'll write over it. So 5 6 for element 1 is local node 2 3, right? For element 1 is
Hmm.
2 3
5, 6 for
plus,
local node 1, 4.
yes, right. Plus we have for second element is 1 4, correct. Then for 6 1, do we have connection? Right, we have.
I have
That is
element 1
3
only, no?
1, 3 1 of element 1.
Hmm.
6 2 is also connected. 6 2 is
6
4
to connect.
2 of element 2. 6 3 is
Yeah.
4 3 of
4, 3.
element 2. 6
3.
4 is 3 4 of element 1.
Okay.
6 5 again is this connection is both in both elements. So we have
4, 6.
one contribution from element 1 and then from element 2. So for element 1, the connection is 3 2. Local node 3 and 2. And for element 2, it's 4 1.
Mm-hmm.
Local node 4 and 5 is local node 1. And again
Okay.
6 6 is
6, 6.
there both elements. So for element 1, for element 2, for element 1 6 is node 3, local node 3 3 3, and for element 2 6 is local node 4 4 4. So this area got really messy, so we have more terms here. Anyway, I hope this is clear, right?
Sir, but I think they won't ask this much. For understanding concept wise, we will
Yeah.
learn. But in examination point of view, I think they want answers. Small box they will be given. No?
Yes,
Uh,
yeah.
So I
In
think,
fact,
yeah.
they would just ask you what is the value of contribution at say element 4 3. They can ask that.
Uh,
Just one or
Acha,
two of these.
we have to calculate it, right? That some small answer.
Yeah, yeah, yeah.
Sir, can we expect that model, like model questions of 5 or 6, like some box? What answer we have to put like that? Yeah.
Model like what type? I didn't
Means
get it.
what I'm asking is, previously so many NPTEL papers are there, na, sir. Previously students also attended for the same exam.
Yes.
From them, any 5 to 6 questions. So, how to we in box how to enter the answer? Because sir told on Monday, sir told 60 questions from online, one bits wise bits, and 40 we have to put the answer in box.
Okay, okay.
So
I understand.
this concept is very nice, sir. We have been following, but 20 for 40 marks we have to put simply answer, na. Like that, any 5 to 6 questions we done it drilled, we practiced. Practice makes man perfect. So like that, I'm requesting you.
Okay, okay. I
Yes,
actually don't have much idea about the content of
NPT.
examination here
Okay,
because
okay.
I just following the course syllabus. I have never actually taken this course in on NPTEL.
Okay,
I
sir.
just watched the lectures, but
Okay.
I've seen the assignments, so I have some idea of the assignment problems that I'll discuss here also. But
Yeah,
regarding final
those things.
exam,
Like a
I'm
model question paper, and
yeah,
like a model questions, what in the box we have to put answer.
okay,
Yeah, this
okay,
concept is very nice. Now we are following. Still you want to go ahead, sir. We have been following you, thankful to you. And if any 5 to 6 like model questions we done, confidence will improve, like examination point of view, I'm requesting, sir.
okay. I'll try to see if I can find any such questions.
Okay, okay, we'll wait, sir.
Right now, I don't have, but
Okay, okay.
as for now, I have some similar questions from assignments on all that.
Like this, just put the answer in the box like that.
Okay, I'll try to do that.
Okay,
I
sir.
think
We have been
that's it.
have been following for previous also, sir told. Okay, sir. Thanks.
Okay, I think this question was all done before. So I think like this kind of question was there, right?
Directly put the answer,
Yeah, yeah,
not the objective type, like blanks. Fill in the blanks like that. They will give one box. We have to
yeah,
put
yeah, yeah.
answers, sir, for 40 marks. If we practice
Okay.
like that, then more interest, more marks. Na? our our merit will be improved. That's why.
Yes, yes. So what I am trying to do is I'll uh, try to do as much as possible in the given question. So if
Hmm.
in the exam anything of that would be asked,
Yes.
you will be able to answer it.
Concept, sir. Yeah, correct,
Yeah,
correct.
yeah. So
I am just asking examination point of view.
yeah, yeah.
Okay, okay. Concept is perfect means we can do n number of questions. So that is
Yeah,
correct,
yeah,
sir.
yeah.
Your methodology. But if
So
we practice, I am practicing, sir. I have the pen and diary. I am practicing with along with you.
okay,
If I was practicing 5 questions like this, okay, I am 42 and associate professor in Saint Peter's Engineering College, Hyderabad. Okay,
okay,
we are getting some hardly time this time. Examinations are happening. Lab. That's why I'm asking, sir. Okay, sir. I'm following, sir. You tell, sir. You tell.
yeah, yeah. Right now, I actually don't have much questions. I have prepared only these, so I'll try to discuss as much as possible with among from these.
Okay, sir.
And maybe next week I'll try to see if I can get any examination
I
question.
think 26th exam, sir. Okay, sir.
Yeah, if you have some previous questions,
Okay.
can you send them to me?
I'll try, sir. I have to check in YouTube. I've been following nicely.
Yeah, if you
Uh,
have some content, just drop
sure,
them
sure, sure.
on
Now,
my
I
email.
will.
Do you have my
Yeah,
email ID?
you can tell, sir, please.
I'll just type it in the chat box.
Sure, sure, sure. Thank you so much. Okay. I think I'm getting mail from you now. Okay, okay. I'll check it out.
I'll just
Yeah, you can drop
type it
that.
in. Yeah.
Okay, okay.
So
Yeah, sir.
I
Thank you so much.
yeah.
Yum.
So if you have any related questions, so if you want me to solve, just share those to me. I'll try to do them in the next class. Anyway, that's going to be our last class probably.
I think so. Okay.
So
Okay,
we'll
sir.
try
We'll practice.
to practice for the exam.
Okay.
Okay. So yeah. So we can move on to the next question now. So we this is the an assignment question, and a very specific thing regarding this was asked, but I'll try to cover as much as possible. So first of all, we want to find the connectivity matrix. So I think we have done enough for connectivity matrix. I can just quickly go along with this. So now we have been given the node numbers already. So the ones given in red here are global node numbers, and one given inside the element are local. So we have four elements in total. So that's why we'll have four rows here. And so for element one, we have total four nodes, four local nodes, right? So we'll have four columns for element one. So the connectivity should be for local node one is a global node one, local node two is also a global node two, and local node three is global node four. And for element one, local node four is global node three, right? Then for element 2, again, the local node 1 is the global node 4, and the local node 2 is the global node 5, and the local node 3 is the global node 3. We don't have anything here. It's a 3 noded element. And then for element 3, we have the local node 1 is the global node 4, the local node 2 here is the global node 7, and the local node 3 here is the global node 5. Then we don't have anything here. And for element 4, we have the local node 1 is the global node 4, the local node 2 is the global node 6, the local node 3 is the global node 7. Again, we don't have anything. So this is the connectivity matrix. Uh, Again, so I'll just copy this thing. So we want to write the okay, this can't be copied here. Okay, we'll just do it from here. So we have to write the stiffness matrix. So we now this is again a practice for us. If we are not given a mesh, right? We are given only the stiffness matrix. Sorry, not stiffness. We are given only the connectivity matrix like this. So how are we going to write our uh, global stiffness matrix? That can be practice it. So since it's a big matrix, we'll try to do as much as possible. We will not do all. Okay. So so first of all, what would be the size of the stiffness matrix here? Other people can also answer this.
Can I expect a 7 by 7? No, 7 by
Yeah, yeah.
7.
So if you look at this B matrix connectivity matrix, the highest number of node is 7. So we have 7 by 7. 1, 2, 3, 4, 5, 6, 7, 1, 2.
So that, sir, uh,
Yes.
so global matrix will be defined by number of global nodes,
Yes,
or
yes.
even freedom, degree of freedom also, sir. Both will be considered.
Yes, yes, yes. Degree of freedom is a better choice of term since we have not gone through multivariable problems. So for now, the number of degree of freedom is same as the total number of nodes for us. But
The degrees.
in case,
If mentioned, then we have to concentrate on degrees of freedom.
yes, yes,
Because
yes, yes.
because if it is constrained means that is zero.
Right, right,
Some
right, 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 right. That's
so
right. So
if dy of degrees of freedom is not given, then we have to take nodes directly. No need to consider. Directly go take what is number of nodes are there. That will decide the global matrix size. But when
yes,
our degrees of freedom is there, we should check it properly and then we have to consider.
yes, yes, yes. Right, right.
Okay, okay, sir. I'm following, sir.
Yeah, thank you so much. So again, we have a 7 by 7 global matrix. So we'll start with row one. We'll see. So first of all, element one, the global node one is part of how many elements? Just look at this B. We don't need to look at the mesh now. So if we look at the connectivity matrix B, the global node one is only found here, element one. So its contribution would come from only element one, and for element one, it is the local numbering is what for this node. So it's at first position, first column of element one. It is the first node of element one, right? And one two. Now for second one two, uh, what connection do we have? So in how many elements do we have one two together? So, so we have only this element one where we have one two together, right? So the contribution comes from only element one, and that is the number, the local numbering would be again 1 2, since both are at, one is at 1 and 2 is at 2 local position, right? So, right, L1, L3, right? Now for 1 3, 1 3 are together in only element 1, right? Since 1 is only in element 1, so contribution would also only be from 1. So again 1, and what is the local node numbering here? Can you tell?
1 4,
Yeah,
one
so
three, 1 4.
right. Yeah, so the 1 is the local node 1 for element 1, and 3 is the local node 4 of element 1. That's right. And 1 4 also we have a connection in element 1 only. So 1 4 is 1 is again local node 1, 4 is local node 3. Okay, 1 3 of 1 element. Now 1 5 don't have any connection, right?
0,
Since, and 1 6 also 0, 1 7 also 0, right?
0.
Then for 2, global node 2, global node 2 is in how many elements? It's again only in element 1. It's not there in any other element. So 2 1 is 2 1 of element 1. 2 2 is 2 is again a second local node of element 1. 2 3 is there. 2 and 3 are both a part of element 1. So 2 at local node 2 and 3 is at local node 4. Then 2 4 is also part of same element 1,
Element 7.
element 1, right? So 2 is local 2 and 4 is local node 3. And 2 5, are they together anywhere? I think not. No 2 6 and no 2 7. Now 3 1. So 3 is there part of it, two elements. 3 is here also and here also. So throughout the entire row of 3, we'll have contribution coming from element 1 and 2. So first of all, 3 1 is only in element 1. Sorry. So 3 1, so 3 is local node 4 and 1 is local node 1. And now for 3 2, 3 2 is also part of only element 1. 3 is local node 4 and 2 is local node 2. And 3 3 3. Now 3 3 contribution comes from how many elements?
12.
2 elements, right? Since
12
3 is
ones.
part of 2 elements. So 3 3, first of all, for element, it will come from element 1, then for element 2. So for element 1, 3 is local node 4, 4 4. And for element 2, 3 is local node 3 only, 3 3, right? And 3 4. So 3 4 connection is there. First of all, it's there in just okay. So 3 4 is part of element 1, of course. Element 1 is there, plus it's part of element 2 also. So for element 1, 3 is local node 4 and 4 is local node 3. And for element 2, 3 is local node 3 and 4 is local node 1. Okay. Now 3 5, less space. So now 3 5 we have uh, 3 5 is connected only in element 2, right? So its contribution comes from element 2, and 3 is local node 3, 5 is local node 2. Now we have 3 6. 3 6 in element 1, 6 is not there. In element 2, 6 is not there. So and 3 is only in these two elements, so it's 0. And 3 7 also 0. Now 4 4 1. So 4 is going to be very it's part of all 4 elements. So its contribution would come from all 4 elements. I think we'll do this one, then we'll stop this question. So first of all, K 4 1. 4 and 1 are connected only in element 1. So its contribution come from element 1, and 4 is a local element, local node 3, and 1 is local node 1, K 3 1 of 1. And 2. So 2 is also only in element 1. 4 2 is contribution comes from only element 1. So uh, for element 1, 4 is a local node 3, 2 is 2. Now 4 3. 4 3 is also connected in two matrices, two elements. First of all, for element 1, then for element 2. So for element 1, 4 3 means 3 4. And for element 2, 4 3 means 1 3. And for 4 4. So what should be the contribution for 4 4? Can someone answer this?
4 4 only is there, sir. Is there 4 4 under
4
1
4 is in element 1, right?
under 1 element 1?
Right. And what else? Which one? So it's there, right, in element 1. we need more space to write this. So 4 4 first of all comes in element 1 and it's at local node 3, so K33. Whereas 4 is in element 2 also, you see here. So it's in element 2 and the local node number is 1, right? And what about element 3 and 4? Is it there in 3 and 4? So the global node 4 is also part of element 3, and again at element 3 it is at local node position 1, and similarly for 4 also it's for local node 4, 1, local node 1. So we'll have 4 contribution for global node 4. And again 4 5 is connected in which elements? You see 4 5 connection is there in element 2, and 4 5 are also connected in element 3, right? So 4 5 will fill the, first of all, sorry, 4 5 contribution comes from element 2. 4 is local node 1 and 5 is local node 2. And again 4 5 contribution comes from element 3, where 4 is local node 1 and 5 is local node 3, right? And 4 6, do we have any connection between 4 6? We have 4 6 connected only in element 4, right? So 4 6 contribution is from element 4, which is 1 2, local node 1 and local node 2. And 4 7, do we have connection? 4 7 also we have two connections. First one is from element 3. 4 is local node 1, 7 is local node 2. And 4 7 is also there in element 4. So element 4, so for element 4 node, global node 4 is local node 1, and global node 7 is local node 3. So K413, K13 of element 4. So this is the contribution for K47. I think similarly we can do for, can we do for 5 6 and 7, right? For 5 we have only it in only element 2 and 3. 6 is there in element 4 only, and 7 is there in element 3 and
Yes,
4.
sir,
So I hope this is also was a good exercise to assemble the stiffness matrix by just looking at the connectivity matrix B. Earlier I had shown earlier we I had shown uh, the mesh also, so it's easier to look at mesh here and fill the stiffness matrix. But suppose if in a problem we are not given the mesh, we are just given the connectivity matrix. So then how will you find the global stiffness matrix? How will you assemble the global stiffness matrix? So this is how it should be done. I hope this was clear, right? Okay, so we can move on to the next problem. So similar to the previous problem, also there was one more problem given in assignment. There was another mesh, a similar mesh that had multiple triangular elements, and again we have to find the connectivity matrix and assemble the global stiffness matrix I think the procedure is same. I think we've done it quite a few times now. We'll take a look at it later if we have time. We can move on to the next problem. Or if you want to discuss this now, you can tell me. Okay, so can we answer this? For the meshes in problem 4 and 5, what is the total number of element level equation, global equation? So first of all, for problem 4, which we just solved, right? So we have this mesh. So how many element level equations do we have?
Four elements.
Total element level equations.
Element level equations. Four elements means total how many equations you're coming? You're asking us, huh?
Yes, yes. So we have four elements. So first of all, let's look at each element, right? So first, for element one, how many equations do we have? So
Four.
the number of equations is equal to the number of nodes in the element, right?
Four
Or the
equations.
number of degree of freedom, as better said, right? So for element one, we have four equations, right? And then for element two, how many equations do we have?
Three equations.
And for element three, we have,
Three.
and also
Four.
for four,
Three.
we have
9
three,
plus 4, 13 equations.
13 equation, right? And how many global equations do we have?
7.
Yes.
Global equation.
Global equations is straight away again given by the total global degree of freedom.
Hmm.
Right. Okay, so can we answer for this one? How many
Hmm.
element
Three.
level equations do we have?
18.
18. So we have, oh, again, now this time we have only triangular elements and we have total six triangular elements. So 6 into 3, get
18
18
equations.
equations.
And global equations 7.
Okay, so we have only 7, not 7 degree of freedom. We have 7 equations. I hope these kind of questions would be asked, would have been asked in exams previously. So we have a problem.
And we have to write simply in the box 13 multiplied by 7, sir.
I'm not
13.
sure. I'm not sure about this. It depends on whatever is asked in the question.
Mhm.
I really don't have much idea, honestly.
Okay.
So for problem 4, we have questions were, I think 17, right?
Mhm. 13, sir.
Sorry, 13.
9 plus
Yeah, yeah.
4, 13.
My
13
bad.
global 7.
I'm just writing it here for, so if someone reads it later would understand.
Yes, sir. Global 7. Next equation 18 of 7.
Okay. Okay, so we are given this kind of problem. So this is a strong form given governing equation, the boundary condition. So what would be the axis of symmetry for this kind of problem? Or how many axes of symmetry can we have here? We are given a circular domain of radius capital R, and at the boundary of circle, that is r equals capital R, we applied u equals 0 on the whole boundary. So first of all, is there any symmetry in this problem? Or is the problem symmetric? If yes, then what would be the axis of symmetry?
The diagonal symmetry is not is taken only quarter, no, sir.
Yeah, so you're saying that we're having symmetry about x-axis and y-axis, right? That's why
Hmm.
like a quarter.
In x-axis, according to x-axis, it may be symmetry.
Yeah, yeah.
Quarter circle becomes semicircle, so that's why quarter symmetry. Y-axis, yes, symmetry. According to x-axis individually, it will be there.
So we have, so we're saying that we have symmetry about this axis, and we also have symmetry about
Y-axis.
y-axis. Okay. Can't we have symmetry about, say, this axis?
Mm-hmm.
Or can we have symmetry about
Infinity answer.
this axis? Yeah, yeah. So for circular problem, we have infinite number of symmetry
Always
axes.
infinity. Correct.
So if we start reducing this problem, suppose say we started s- by bifurcating into a semicircle. We'll have this domain. Now again, this problem is symmetric about this axis. So now we are left with only this much. Particle we are left with this much. Now again, if we can take a symmetry about this axis. Yeah. Again, we are left with this much. Here again, we can take symmetry about this axis. We'll be left with this. Again, we can take symmetry about this. We'll be left with only this area, and we can keep on going on until we are left with a line that is starting from r equals 0 to r equals to capital R. And that's why so you might have seen some many places, or even I think it was done in the last course, basically of FEM part 1. Sir did this. Sir wrote a circular heat conduction problem and reduced it to a 1D problem. So you might have seen at many places that such a circularly symmetric problem are can be translated into a 1D problem, uh, ranging from the center of the circle to the radius of the circle. Okay, so this is how such problem can be reduced. I hope this was clear.
So now answer is what? Infinity.
Yeah.
But sir, one small doubt. I studied about weak form, strong form.
Yes.
That means given continuum equation, weak form, strong form. Can you please tell me one suggestion, sir? Please, I am requesting you because I studied weak form continuum equation. Whatever equation is given, weak form, strong form. Can I request you, sir, to tell again once?
Yeah. Sure. Sure. I'll try. So basically, the given differential equation
Okay.
for the governing equation, that is the differential equation for the problem,
Hmm.
like this.
The first order. Hmm.
This is called plus along with the boundary condition. This whole definition of the problem is called the strong form. I'll make it interesting. I'll write du by dx at x equals to 1. So such kind of definition of the problem is called a strong form. The basic differential equation that we see.
It
Uh,
means boundary condition is given perfectly.
yes, yes.
U 0, 0.
But if we take the weighted residual statement and
The previous question is in a weak form. Yeah, circle form.
this is strong form given here.
Mm-hmm. Is given the boundary condition. Okay.
Yeah. So if we take the weighted residual statement and we perform integration by parts,
Mm-hmm.
if we performing integration by parts basically transfers
Mm-hmm.
this differentiability from the our primary variable to our weight function. So basically, the differentiability requirement for our primary variables reduces. So the term weak in this the nomenclature here basically means the differentiability requirement is weakened. So and in FEM we assume a solution. So we assume some function, some polynomial usually for u, right? So weakening this differentiability requirement allows us to choose a lower order polynomial,
Mm, AX plus B, like that.
right? So if it would
Single
have
ordered.
been a second order derivative on u, I would be forced to choose this function.
Mm.
But since now it's only a first order derivative, I can easily skip this term and use this. There won't be any issue in the formulation, or there won't be any numerical issues in the formulation. So this is basically the motive of weak form. Plus, there's one more thing that when you write the weak form, you are also left. You also get a boundary integral term, or in I'll write in terms of 1D. Since 1D we only have 2 points at boundary, 0 and 1. So we uh, we can expand this term as, since we know the value of u at 0, so at that point w becomes 0, so this term would be, I'll just expand it, w uh, I can expand this as value of w at 0 and value of du by dx at 0. Sorry, this is 1 minus 0 at 1. Value of w at 1 and value of du by dx at 1 minus value of w at 0, value of du by dx at 0. So since u is known as at 0, w, this term goes to 0. And since du by dx is known at 1, we are left with this term, value of w at 1 times this 1. We can substitute it directly. So in this sense, our Neumann boundary condition is also incorporated in the weak form. We don't need to separately specify the Neumann boundary condition. If we see this equation, we can straight away tell what our Neumann boundary condition is. Of course, we have
Yes,
sum
sir.
also. So this is basically the purpose of weak form. Okay,
Yeah, okay, sir. Okay. Thank you, sir.
no problem. So I think we had some more problems to discuss, but I think we are out of time now.
Sir, one more question, please. You are showing now. Just one more.
Yes,
Down,
yes.
down, down, sir.
Please,
Just
please.
one last. We'll finish with this one. Yeah, yeah. Calculations. Last, sir, please.
Okay, you want to me to discuss this? Okay, okay. Okay, I hope others are okay with extending some time. So I'll try to finish this as quick as possible. I'll
Yes,
also
sir.
do my
Yes, sir.
best.
We'll finish it by this way. Last.
In the Jacobian. Okay. So we are given this quadrilateral. It's basically a square. Connect the nodes. Node 1, 2, 3, 4. 1 is 0, 0. 2 is 1, 0. 3 is 1, 1. 4 is 0. Excuse me.
Okay.
So find Jacobian. So first of all, we want to find the Jacobian, right? So what is Jacobian? Jacobian is dou x by dou zeta, dou y by dou zeta, dou x by dou eta, dou y by dou eta. Isn't it? Then, so in order to find the Jacobian, we want to find x as a function of zeta and eta, and y also as a function of zeta and eta. And for that purpose, we have this formula: x is summation of I psi I times xi, right? So psi I
Hmm.
are the shape functions. So for
Okay.
quadrilateral elements, so these are shape functions for the standard quadrilateral element, which should be like this: minus one, and one common. So standard shape functions, I think formula is given as 1 by zeta by 2, 1 minus eta by 2, and similarly for 2, I think it's 1 plus zeta by 2 times 1 minus eta by 2. Psi 3 is 1 plus zeta by 2, 1 plus eta by 2, and psi 4 is 1 minus zeta by 2, 1 plus eta. I think these are shaping. Just verify this once. So we psi 1 x1 plus psi 2 x2 plus psi 3 x3 plus psi 4 x4. So we can, so we, for x1 is 0, psi 1 terms goes, x2 is 1, so we are left with psi 2, x3 is 1, so we are left with psi 3, and x4 is 0, so the term also goes away. So x equals to psi 2 plus psi 3. If you add up psi 2 and psi 3, do they have anything common? No. Psi 2 and psi 3 don't have anything in common. So you get the idea. You can just substitute the value of psi 2 and psi 3 and get
Hmm.
shape function of eta and zeta, right?
Yes, sir.
Similarly for y also, it's summation I psi I cap to be consistent y. So that's equal to psi 1 y1 plus psi 2 y2 plus psi 3 y3 plus psi 4 y. So y1 is also 0, psi 1 term is gone. Y2 is also 0, psi 2 is gone. Y3 is 1, y4 is 1. We are left with psi 3 plus psi 4. Again, if you substitute the value of psi 3 and psi 4 from here, you'll get some function. I think this is easier to predict. 1 by eta by 2 would be common. Then 1 plus zeta by 2 and 1 minus zeta by 2, it would be just 1. Okay.
Yes, sir. So finally, answer sir, 1 plus zeta by 2. Huh?
1
So we
plus
can
zeta
calculate
by
those
2.
values and keep in y1, y2 it comes.
Yes, yes. You'll get the value of x as a function of eta and zeta. You take the derivative with respect to eta and zeta and the substitute here. Again, you get the value for function for y. Just, you take the derivative with respect to e times eta, substitute the value. You get the
Okay.
Jacobian matrix. You can take the determinant also in order to check. You can also verify that it's a valid Jacobian by taking the determinant.
Mm-hmm. Okay.
Okay.
So delta of okay, so okay, so delta of 2 by 2 matrix will come. No? Okay.
Yes, yes, it will be 2
Okay.
by 2
Okay.
matrix. For 2D, it's a 2 by 2. Okay, so I I hope there's no further doubt here. Uh, if there's any doubt, you can let me know.
Sir, how will come to the assignment marks? How much we get like that?
I think you will get to know later. Probably. By the way, assignment solution is given immediately. I
Hmm.
think. I think
Okay.
after
Cross
submitting
check
the
myself, ourselves.
yeah,
Yeah, yeah.
you can just open the assignment in the
Okay.
your
And
assignment
cross
section
check.
in your
That's retrospection.
yeah.
Like a retrospection, we can check it and see check it. Okay, sir. Okay, sir. Thank you
You
so much.
open the page where you submitted the assignment, right? If
Hmm.
you open
Hmm.
that page, you will get to know
Yeah,
what you
yeah.
answered and what the correct answer is.
Hmm. Okay, sir.
So you can get your marks right now. All right. So are there any more doubts? Okay. So if there are no more doubts, then we can conclude the session now. And
Okay.
yeah, so I thank
Okay.
you
Okay.
so much
Thank you,
for
sir.
joining the session today, and we'll meet again in the next session for week 8. Next week Tuesday at 7 p.m. again.
After exams, huh?
Sorry,
Exam is on 26th March, no?
is it?
Yeah.
Ah,
I have exam.
26th March.
So I have this schedule the session like this.
Achha, achha, I can participate. Okay, we can participate.
Anyway, I'll just confirm with the NPTEL team once. I don't know why
Okay.
have they kept the schedule like this.
Okay, sir. Okay,
Or
sir. Thank you.
yeah, I'll just confirm with them once. Okay, then we'll
So
conclude here.
thankful to you, sir.
Yeah,
Okay,
thank
sir.
you so much. If there are
Okay,
any
sir.
queries meanwhile, please you can. I've given you my email.
Hmm. Okay, sir.
Okay, thank you so much. I'll end the call.
Okay. Okay. Good night.
Good night.
Okay, sir. Okay, sir.